Our presentation is on slope failure and landslides. I'm Jamie Martell.
I'm Taylor Liasca.
I'm Pat Fanning.
Pat Day.
Brian Smock.
Andrew Sampson.
I'm Sean Brennan.
I'm not sure if any of you know this, but I used to enjoy living on top of a mountain, but after a recent landslide, everything's kind of gone downhill.
Alright, so downslope movement of material can be quite unpredictable. However, it can also be correlated to the steepness of the slope. So obviously, if you have a steeper slope, material is more prone to slide down relative to a gentler slope. And this idea also corresponds to the rate of movement. Things are going to travel faster down the steeper mountainside. And the idea of slope failure is dependent on two main forces, the driving force and the resisting force. So a driving force is anything that lets material slide down slope, and the main one is gravity, but can also be anything like the steepness of the slope, as mentioned before, and the material that the slope is comprised of. Resisting forces, on the other hand, prevent movement of material downslope, and the primary one is the shear stress of the rock or soil. The factor of safety for slope stability is viewed as the ratio of a resisting force over the driving force. So if you have a factor of safety greater than 1, it's a safe slope, and most factors of safeties are used as 10 or above for building design to compensate for the loads that are going to be present during construction, and a factor of safety less than 1 is often leads to a mass wasting process.
So there are a couple different types of mass movements. The first two, which are falls and topples, consist of failing rocks and soil due to shear stresses. Falls occur when the rock fails and falls directly down to the bottom of the cliff face, whereas topples rotate around a pivot point and then will roll down a cliff face. Some other types of mass movement are slides, spreads, and flows. Slides have a distinct zone of failure, and this weakness causes it to slide down in one mass of bedrock and soil. Spreads occur during seismic activity and other vibrations that cause the soil to liquefy, and this causes a lateral spread of the soil and debris. And flows occur when the soil becomes a viscous fluid and will flow in one mass downhill.
So as we've already talked about some of the background about certain areas that are prone and why they're prone, there has to be triggers that cause landslides, and usually there's not just one reason why slopes fail or landslides are caused. Earthquakes are the main trigger of landslides, as seismic activity can cause soil to shift and it causes the soil to become unstable. Rainfall, as Brian talked about with the water in the soil, can decrease the intersoil friction as heavy rainfall, the soil becomes saturated and it reduces the soil cohesiveness, and it will decrease the angle of repose, and so it makes that soil more prone to a landslide. Clear cutting, as you can see in this picture, this is a mountainous region that has been clear cut, and when you have a lot of vegetation on an area or a slope, the roots of this vegetation, whether it be like brush or like trees, it helps maintain stability in the soil as the root gives it sort of stability and like structure. And so when you clear cut an area, it destroys the mechanical root structure that helps keep the soil stable. And also mining is kind of similar to earthquakes in terms of like the blasting techniques create vibrations that cause sliding to happen in like areas of soil that are risk prone. And just a few parameters to look for when you're monitoring mass movements is that there might be ground cracks, or that there could be an appearance of like upheaval or subsidence of the soil. So like when these triggers happen, those are like a few things that you can look for in like landslide prone areas.
Okay, for our first case study, I looked at the South Mountain Road Slope Stability Study. Back in the 1970s, Hong Kong was having a lot of issues with slope failures due to heavy rainfall in the area. And as you can see here in the picture, there's residential buildings and a road at the bottom of the slope, so the slope was a primary concern. For the analysis, since they didn't have a lot of slope stability modeling programs back in the 1970s, they simplified the analysis to a two-dimensional diagram you can see here. The overall angle of the slope was at 50 degrees, and then at 35 degrees you can see the exfoliation joint where the slope could possibly fail. And also another important thing about this diagram is you can see the top right is that there's tension cracks. These tension cracks can fill with water, and the pore water pressures that arise when water fills the cracks can push the slope, and these forces have to be taken into account. In the bottom diagram, you can see how they modeled the slope and the forces acting on it. Along the bottom side of the slope, there's a pore water pressure pushing the slope up at an angle, and then at the top, they did one analysis including the force due to the tension crack water, which is that horizontal force at the top right. And in addition to these forces, they accounted for minor earthquakes by putting that alpha W force you see there, which could cause the slope to fail. So in the end, they had some short-term resolutions that were made. They decided that they didn't need to evacuate anyone, and also as preventative measures, they were going to drill holes in the side of the slope to remove some of the pore water pressure acting on the slope, and also they were going to install piezometers at the top of the slope to monitor the saturation of the soil during heavy rainfall periods. As a final solution and a long-term goal, they decided from this diagram, you can see here, decision 3 on the left had the desired factor of safety of above 1.5 with the lowest percent change to the slope. So they decided to go with that decision, and it was to excavate the slope to the 35-degree angle exfoliation joint where the slope could fail.
So for my case study, I did the 1994 Northridge, California earthquake. It was an earthquake of magnitude 6.7 on the Richter scale. It affected the Santa Susana Mountains and north of the Santa Clara River Valley. This is kind of a unique example because it's an earthquake that caused over 11,000 individual landslides over an area of 3,000 square miles. So for example, this picture here before the earthquake used to be completely green and covered in vegetation. All the white areas you see are individual landslides. This is because the mountainous region here was composed of very weakly cemented sedimentary rocks, so essentially sand just piled in the mountains. When you induce vibrations into this, it becomes liquefied very easily and acts like a fluid. So because of this, you have most slide style landslides. There were some slump and block slides due to the different regions. A better example, there's a wide range of landslides from very small to very, very large. The right circle is a person for scale, and the bottom vegetation, the top vegetation with the star, and bottom of the landslide. So there wasn't a lot of damage, and there weren't any human deaths caused by the landslides themselves because this was a very not densely populated area. There was some road damage, as shown on the left. Road cover took a couple days to clear out. A rock fall on the right. There was also some water pipeline damage, and a local oil refinery was damaged throughout it. The one home that was damaged was essentially split in half due to the landslide. The slope below it gave way. And an interesting factor of this was there was an outbreak of valley fever due to the large dust created by all this very sandy landslide, and there were very toxic fungal spores in the dust that, when breathed, caused a few cases of valley fever.
For the third case study, it was in Oso, Washington, and it was the Oso landslide, also known as the Steelhead landslide. It occurred on March 22nd in 2014. It was considered one of the most catastrophic landslides of the past few decades. 43 people died, along with very large area of homes and residences and farmland. So the failure area was about 450 meters by 500 meters wide initially. It grew up to be 7.6 million cubic meters and traveled over a kilometer. So some of the causes of this landslide were, in this area, there's a long history of slope instability. There's been 5 other previous catastrophic landslides. During this time of year was the winter, and the precipitation was unusually high, so the rainfall saturated the soil and uprooted a lot of trees. Due to the landslide composed of glacial sediment, sand, and silts, the landslide grew at a big volume as it hit the North Fork River, and it grew, and the volume took down and was able to take out a large section of area. So, as you can see at the crown in this picture, in the crest, rotational failure happened at the top of this landslide schematic. So the landslide started to slip along the cracks in the crown cracks down the side along the curved surfaces. So some preventions that could have been made to help prevent this, or in the whole region of this area, was geological assessments should have been taken for the slope stability in the first place. This would have resulted in denial of a subdivision put right beneath of this landslide, as you can see along the whole road and the river of this section, which ended up being completely demolished. Along with, there could have been reconstruction of the slope, which also includes subsurface drainage and diversion structures to help move and push the water and slope in another direction.
So basically, landslides are caused by liquefaction of the soil, and that's when soil loses its strength and starts to flow like a fluid. And then this is driven by gravity, which will just pull all the soil to the ground, and due to the mass of all this soil, it can cause a lot of damage and kill a lot of people. And this is usually triggered by intense events like earthquakes and heavy rainfalls, and this then can trigger liquefaction of the soil, which then causes the landslide. And in conclusion, there's thousands of people die every year due to landslides, and billions of dollars are spent on property damage. There was $1.5 billion cost in the U.S. alone. And this is because it's a very unpredictable event. It takes a lot of geotechnical analysis of the soil to realize that the slope might be prone to it, but it usually happens in areas that are already developed, and therefore people kind of think that the soil is going to be okay, kind of don't really think about it. But there are some ways to prevent landslides. Like I said, intense geotechnical analysis before you build on it, and then surface and subsurface drainage helps a lot. Retaining walls at the toe or at the base of a steep slope, and then piles or just support of the toe can really prevent landslides from occurring.
Questions? Nobody has any questions?